Hello there, math fans. I'm going to give a replacement lecture for double integrals over polar regions, but I'm going to do one of my favorite examples of the shape you get when you take a cylinder and you intersect it with a plane that goes right through the middle here. And this volume you get. I've done this example for years. It was on an old final. I really like it because it illustrates all of our different methods. And then I just recently looked up the history of this. So this it's sometimes called, and I'll talk about that stuff on their left, but it's an interesting problem. We could call this a spherical wedge, but I never had heard the following term before, which is that if you take a volume of revolution and cut it by a plane, it's called an ungula. I don't even know if I'm saying it right, which means an animal's hoof. Supposedly this exact shape, played a real essential role. I found in one place a historian saying that studying this shape was an essential shape and leading to some of the integral calculus techniques. So an ungula played an important role. I didn't realize that. So we're going to find the volume of that in a second. I'll show you some visuals, and I'm going to use this as a recap of chapter 15, and I find that as a good jumping off place for doing our lecture on polar. Okay, so everything in chapter 15 essentially fits into this. You have some surface that's given. My surfaces always look like flying carpets. And you have some region on the ground. And we've seen how to deal with general regions, and we're finding the volume between them. It isn't so much that volume's the most important thing, it's the fact that you're learning how to measure things over a region. So it's all really, I feel like chapter 15 is about learning to measure, like if you wanted to know the average temperature over a region, or you wanted to study the flux across a region, those are things where you would need to describe a region. So that's really what we're practicing, is those skills. Volume is just a convenient place to practice it. Okay, so we have learned two ways. You can do it in terms of x, you can do it in terms of y, and then we're going to add something to your toolbox that's especially good when you're dealing with something that's stated relative to the origin, when it's a polar region. And when it's a polar region, especially if it's a circle, this tends to be much better. But there's a few things we have to talk about. So I'm going to do this example, and I'll probably do another video where I talk about the theory of where this comes from. The hardest things to remember is you have to think in terms of polar to describe the region. You have to change everything into r's and thetas. And then the fun part is the dA, you have fundamentally changed the geometry. You get to talk like a pirate. R, d theta. I was trying to see if I could find an eye patch, but R, d theta. Okay. Sorry. Okay, so I'm just going to do an example, and then we'll talk through. This is how I like to do this. Let's see how we're actually going to use this, and then we'll go through and talk about what in the heck is going on here. Okay? So consider this problem, and let's run through the process. Step 1, the volume says it's under this plane. That is the only z I see in the problem. There is a mention of the xy plane, which is z equals 0, but that's what a double integral does. So step 1, are there any z's? Yes, there's one. Plop it in here. And there are places you need to visualize and think about it, but honestly, you can do a lot of these things mechanically. So I'm trying to help you get going here. Second, you're going to draw the region on the ground. Now on this exam, they provided a picture, which was very helpful, because if you just didn't have the picture, you would have said, okay, inside this circle of radius 3. And if you integrate over the whole circle and keep going, you would end up with 0. And I always hope that if students see this picture and they get a volume of 0, that they know that something's wrong. And so then you have to think about what in the world? And so we just did this. We drew the given xy bounds. When you find yourself confused or doesn't make sense, then you do this other step. The surface must hit the ground. Does the surface hit the ground? So when does z equals x intersect with z equals 0? They intersect when x is 0. So I don't want to go past when x is 0. I see, I only want to do here. And that matches up with what I'm seeing in the picture. So, like I said, I like this example because I feel like we get to do a little bit of everything. We were given x and y bounds. We had to use the fact that the surface intersects the ground. And now we're ready to go. So now we have the region. And we have this. So then we switch to describing the bounds. So again, this is why I like this example, because we get to do all three. So when I do this in class, we do all three. You could do it in terms of x, you could do it in terms of y, or you could do it in terms of z. And all of them work reasonably well here. So I'm going to do all three labelings. And I do think that it's mostly about your ability to label. That's the challenge. And that is a very important skill. So if you find yourself fuzzy on labeling, come to the Math Studies Center. Sorry, I scrolled. My screen does that sometimes. Okay, here we go. So here's how we're going to label this. First, we could label x. So I'm labeling a random x in the region. Second, we could label y. And then we have this new thing, which is that we could label theta. Theta being this angle. And then for each of them, we would try to find a pattern for how far to go from our given labeling. So based off of x, can we find how far to go from here to here to mow the yard, so to speak? So can I find this y value? And can I find this y value? If I'm using y, then we're going to ask the following question. How far do I need to go to get to the corresponding x? Here and here. And if we're doing polar, we're going to ask the following question. What is this r? And what is this r? I think of this first one as top-bottom. I think of this one as right-left. I think of the last one as inside-outside. Those are our three methods. So when I look at this, what I see is, and I can immediately set up the outer bounds. The biggest and smallest x can be is 0 to 3 dx. So that's one option. Maybe I'll do a better job of my spacing here. So this first option would be the integral from 0 to 3 dx. How do I know that? I just look at what's the biggest and smallest x could be. The second one would have been the integral. The biggest and smallest y can be is negative 3 to 3. And lastly, the biggest and smallest the angle could be. So you think about rotating, they have to be consecutive. I know that down is typically 3 pi over 2, sorry. But you cannot say this because it doesn't make any sense. And you'll get a negative. So if you're going to say 3 pi over 2 here, you have to say 5 pi over 2 here. Or as I would prefer, I'd like to say negative pi over 2 for when I'm down to pi over 2 for when I'm up. All three of those things are fairly easy to do because you're just saying what's the smallest x, what's the biggest x, what's the smallest y, what's the biggest y, what's the smallest angle, what's the biggest angle. Now comes the pattern finding. Can we find a pattern based off of x? Can we find a pattern based off of y? And can we find a pattern based off of the angle? And the angle is the best one, if you haven't caught on. That's this example. But all three work. All three compute the answer. That's the game. Okay. So the biggest and smallest. So these are both points on the circle. So I need to take the equation for the circle. solve for y in terms of x. Y equals plus or minus the square root of 9 minus x squared. And I'm using both, the negative y and the positive y. So it's from the negative square root of 9 minus x squared to the positive square root of 9 minus x squared. And the integrand hasn't changed, it's still x from up here. That's one correct setup. I don't really love it because the bounds are kind of gross looking. Next correct setup. What if I take the equation for the circle and solve for x? And these are these little bits of pre-calculus that get people. So let me make a little note here. If I solve for x, I get plus or minus the square root of 9 minus y squared. But if you look at that circle, what part of the circle am I talking about? The negative x part or the positive x part? Just the positive x. The left bound is x equals 0. So this is going to be 0 up to the square root of 9 minus y squared. And this becomes x. It's still x. That's also correct. And I always encourage my students, if you want, compute both of these. You'll see that they're the same. And then finally, there's the polar viewpoint. So the polar viewpoint is, if I just walk straight out, when am I in the region and when do I exit? Well, I'm immediately in the region, and I exit when I get 3 units out. And that is lovely. Working with the circle and polar, this is the way to go. But there are 2 things that we'll find out we have to do. First, we have to do r d theta. We've fundamentally changed the geometry. This is kind of like when you do a substitution in one variable calculus. We're actually substituting in for both variables. And when you do that, there's an adjustment. And for polar, this is the adjustment to get the geometry right. There's a whole theory to this, but that doesn't happen in this course. It happens in Math 224. But I will give some of the theory in a moment, or in the follow-up video. And then separately I have x, but I need to switch x to polar. And in polar, x is r cosine of theta. So you end up with an r squared. That's what you do. Now the only downside of the polar is you're going to have to integrate trig functions, and for some students that's hard, but actually that always is not too bad. Sometimes it's a few steps, but it's better than integrating these radical functions, in my opinion. Okay, so here is this shape, this ungula, this volume. We are considering it in a few different ways. So I'm going to show you, if I get rid of the sides there for a second. The 3 things we're considering is, what if we do it in terms of x? So I'm going to do an animation of this is in terms of x. Notice the bounds on either side are both on the circle, and we would be finding the area of those cross sections. Alternatively, we could do it in terms of y. Now, if you do it in terms of y, it's like this triangular shape. I think that could be done without doing the full 126 method. That's what you get. And the last method is polar, kind of radially thinking about the area. Now you can't just find the area of those and then add them up, because that would overcount the volume near the center, and that's the adjustment we have to make. But you get the idea of, we're either going in terms of x, in terms of y, or polar. That gives us these 3 options, and we really need all 3. Okay, that's the idea. So I like that example to illustrate that. So I may stop there and say that we will do some of the other details in class, because ultimately now we just talk through what this looks like in general. And at that point you just compute. It doesn't change the way you integrate. So if you're integrating this, it's going to be negative pi over 2. Pi over 2. There's an r squared. And so when you integrate that, it's going to become 1/3 r cubed. The cosine comes along for the ride. You evaluate it from 0 to 3. So nothing really changes in our evaluation step. You just have another option. And when I plug this in, I get 3 cubed, which is 27, divided by 3, which is 9. And then I'm integrating cosine. And so I get 9 times sine of theta, from negative pi over 2 to pi over 2. And so I get 9 minus negative 9. I get 18. It's the volume of that thing. So that's the volume of that ungula. And let me know in the comments if I made a mistake there. Or you could compute it the other ways. Okay, so the actual method, the polar method, doesn't change. The point of that is it doesn't change really anything we've been doing. It just gives us another option. So the things we have to review in 15.3 first are, can we describe polar regions? Which I think we can. That's what we were practicing. And then, can we remember to do already theta? And then we do need to review a little bit of techniques for integrating trig. Okay, so in terms of regions, it's this new way of thinking. So this sort of explains why I'm teaching polar the way I'm teaching it, to get you ready specifically for this. So like this picture, I would say theta is between pi over 4, and that's because it's the y equals x line. Sometimes people say, what if you were given a different line? Well, then you'd have to do a little bit of trig to turn the slope into the angle, but since that's a 45-degree line, I already know it. And then r is between 0 and 5. So I usually just do these quick exercises. I say, okay, what are the bounds for this? And you would say, oh, I'm going to go pi to 3 pi over 2. And when I'm looking in this direction, r is going to go from 3 to 4. Sometimes students say, why didn't you use negative r's? You could use negative r's, but then you need to look the other way. So if you're looking in the direction you're going, then you need to use positive r's. Okay. When it talks about one loop of a polar curve, what they mean is they want to know when r equals 0. Consecutive times when r is 0. So this is the downside, is you have to do a little more trig. So in class I always talk about, do you know how to solve when r is 0? And I find that students have varying degrees of experience with this, but if you want to know when cosine is 0, you think about the unit circle, and that would be when this is ... And I like to give the first few negatives and positives, but really you just need to remember 1. How about pi over 2? How about 3 pi over 2? How about negative pi over 2? And then what you do is you say, well, it wasn't a question mark. I know what it was. It was 3 theta. And then you divide everything by 3. Negative pi over 6, pi over 6, pi over 2. And here are 2 consecutive times. This angle, which is negative pi over 6, and this angle, which is pi over 6, when you're in this region. So if somebody was forcing you to integrate over that region, you could say, I want to think about the angles between negative pi over 6 and pi over 6. And then based off of that, I want to walk to the edge of my curve. So r goes from 0 to the edge of the curve, which is 6 cosine of 3 theta. So this kind of pushes us a little bit because it's not a circle, so it's not quite as pretty. But if I wanted to integrate over that, erase this, I would do the double integral from negative pi over 6 to pi over 6, from 0 to 6 cosine of 3 theta. I didn't tell you an integrand here. That would have to be given, and then you'd have r d theta. That's how you would integrate over that region. So you have a couple of these in the homework that make you think about a polar region. And so that's kind of, it's a little bit of a 10.3 question and also a 15.3 question. So if you are struggling with describing the regions, that's one thing, and I just want to separate that from the other things we're doing. So like this homework question says, describe the region in the first quadrant between the circles. So it wants you to do this region. You're going to want to convert them all to polar. And you're going to want to convert this to polar. And then you're going to need to figure out the angle when it starts and the angle when it ends, which I've just labeled. And then based off of that, figure out what are the inside and outside. So this problem really makes us think about inside and outside. And I'll probably do one of those in class when I return from the break. So I might kind of stop this lecture here. I have a bunch of pictures in these notes if you're still struggling to think about polar curves, but I also did some of that in the last video. So the actual theory is here. If you want more details, you can read the text. But ultimately what we're doing, if we're using polar graph paper, if you're using regular graph paper, the area of a region on the ground is this, and this is sometimes what we call one volume element. And when we're approximating, we're doing the area on the base times the height at one of the points in the region. If you switch to polar graph paper and you're thinking about change in r and change in theta, there's a major distinction, which is both of these were lengths of the sides of the bottom. And so it makes sense that the area of the base is this length times this length. That's a rectangle. When you're working with polar graph paper like this, you get this is kind of an exaggerated version, but you get a whole bunch of these little shapes that look like that. This is not a length. So multiplying those two does not give you the area of that shape. I've had some classes where I go through this in extreme detail, but I'm going to give you the short version here and tell you, you can ask me if you want a longer version. So the short version is this. And I usually do a quick recap. It always just depends on people's backgrounds. I often start with, how far is it all the way around a circle? So if your angle is 2 pi, what is the distance around? And I try to, this is just to review the connection between angle and distance. So this is 2 pi times r. What if you only go halfway? Well, then the angle is pi. And the distance would be half of what that distance was. All right. What if you only go a quarter of the way? Well, then you get this, and it's a quarter. What if I just give you an angle and the entire distance is 2 pi r? How would you figure out how to adjust this? Well, you would take the angle and divide by 2 pi, and that would tell you the fraction of it that you're doing. So if you think about this, dividing this by 2 pi tells you it's half of the circle. Dividing this by 2 pi tells you it's a fourth of the circle. So what you need to do is divide this by 2 pi and then multiply times the circumference. So the distance around the edge of a sector of a circle, it's theta times r. In fact, that is the reason that we do 2 pi around a circle. That's the reason we made this choice at the beginning of your pre-calculus career. If we use radians, then theta r is the distance around an edge of a wedge. So if this is theta, and this is r, and this is r, then this length is theta r. But only if you're in radians. Okay, so why am I saying that? The question becomes, how do I turn this little change of angle? So what if this is the change of the angle? Just a little tiny angle here. And I want to know the length along the edge. What do I have to do? I have to multiply times r. That's the arc length formula. Theta r, or r theta. If I then want the area of this piece, and this is the change in r, then the area of this will get closer and closer as you get smaller and smaller to this length times this length. Now I've done this more precisely where I use the midpoint and I showed that how it approaches. But the point is, hopefully I've given you enough to say the reason you multiply times r is because when you multiply the angle times the r, you get the length of one of these sides. And so the area of one of these approximating pieces is the change in r times the change in theta. But we don't say dr r d theta because it doesn't sound like a pirate. No, we do arrange the d theta and the dr at the end, and so that's why we say r dr d theta. And the pirate stuff is just something I made up. Maybe other people do that. We never really have, I've never seen d theta come before dr, because that would indicate that we're finding the angle based off of the distance from the origin. But anyways, so this fundamental piece is that it changes the geometry in a way, because the theta is not a length, but by multiplying times r, it does give the length. That's why that extra piece is in there. Okay, I think I will stop there, and we will continue this lecture when I return from vacation. And that part of the lecture will involve me doing examples. I like this classic example about a sphere and a circle, but let's leave it at that. That's enough to get you really going on all the homework, especially if you want to get ahead. I hope this is helping.